Hey guys, welcome back to another video. Today we're going to be looking at Gantt charts, which are what we use to find out the amount of workers we need for a job, going back to our activity networks, finding our critical path, putting our critical path on the Gantt charts, and then finding the non-essential activities underneath and finding how much time we need and how much float time we have to reorganize those non-essential activities to find out how many workers we can have at the job site at once, all working. We want to find the minimum amount. But before we get into that, and before I explain all of that, let's get on with a starter. So here's the starter here for you. This is a precedence table. Go ahead and pause the video and draw an activity network for it and find the ASAP time, the critical path, using the forward and backwards path method. Alright, so once you've got that, we can go ahead and use this information to create Gantt charts. So this is what's required for merit. We want to work out the least number of people required to complete the project and how long each person would be working for. So this is very useful in real life. If we had a building project, we'd want heaps of people. We wouldn't want heaps of people standing around doing nothing. It would be a waste of money. You've got people there that are just standing there, not digging holes, not doing something. You're just paying them money to do nothing, and that's definitely not what we want to be doing as a project manager. We want to be getting the most out of our money by paying people to do things in the least amount of time. And this is where the Gantt charts become useful. So we are going to create Gantt charts to help us work out the minimum number of workers we need. So a Gantt chart has a timeline up the top from 0 until the project completion time, the ASAP time at the end. That's because that's the maximum amount of time that we should be spending at a project or at a job. So we can draw the activities that are in our critical path first. This might not make sense at the moment, but it'll all fall together once we have a look at what a Gantt chart actually looks like. So these activities that have no time for delay. So that's the critical path, the ones that if there's a delay in the critical path, it means the whole project will take longer. So we want those ones to be at the top, and we want those ones to not get delayed, and hopefully do all the other things below, all the other non-essential activities in the required or in the amount the critical path takes as well. So let's do an example from the starter question that we had a look at before. So the non-critical activities, once we've drawn all the critical activities at the top, so the critical path analysis, we want to draw the non-activities at the bottom. These are the activities that have slack or float time. This means that they can start a bit later and it won't affect the project, whereas the critical path analysis, the critical path, if they have any delay time, they will affect the whole project. These ones won't. They have a little bit of float time, is what we like to call it. Okay, so let's have a look. So this is what you'll have from your forward and backwards path methods, and you should have your activities on the lines, and you should have for B 0, 0 at the start, and then B takes 3 days or however long it is, and then it'll take 5, like when you're working back, it'll come to 5 on the backwards method, giving us a float time of 2 days. So the first box tells us the earliest we can start, right? So we can start 0 activities at 0, and we can start B at 3. And then the second box here tells us that latest time we can finish it. So at 5 days we can finish this activity of B. So using our example, we can see that B actually only takes 3 days, and we have up until day 5 to complete it. So we could start it at day 0, and as long as we finish by day 5, we could technically start at day 1 or day 2 as well. So if we were to draw this out in little boxes as representing the days, so this being 0 days, and then 1 day, 2 day, 3 day, 4 day, so on, B would take 3 days to complete. So we could draw a box that is 3 days big, right? And this would be B here. And then the latest that B could finish is here, 5. So we kind of can shade in this little section here, showing how far B could move along until it can finish and not affect the critical path analysis, critical path and the different project time. a whole project done. So effectively, we can slide B along this bar. It could start at day 1, it could still finish on time, or it could start at day 2 and still finish on time, or day 0 and still finish on time. So if you had a look at it, if you visually, you could slide this along like this, right? Back and forth, just like this. It could start at day 0, day 1, or even day 2, and it would still finish by day 5. Alright, so let's have a look at this activity. This is the one, an example from before the other slides, and let's go through and draw the Gantt chart for this whole activity network. So what we want to do, our first step is, if you've got a grid book, it's actually really helpful, but what we need to do is we need to draw a critical path along the top. So our critical path here is highlighted, and which you probably have already found in the last videos or working through the last examples. So up the top here, we've got A, which takes 5 days, and then we've got C, which also takes 5 days, and then H, which takes 7, and then we've got from H, we've got J here, and then we've got K here, which takes 4. So for example, activity A must start at 0 and end at 5 in the order for the ASAP time to not change. If it took any longer, we would be waiting on it and the whole activity would take longer. We need to add the other activities to make up the critical path as done. So like you can see, that's what we've done. We've put the critical path in at the top because that's the longest amount the project should take. Okay, so let's have a look at B. We can add in B here. This line being here, it starts at 5 and it takes 3 days, but it could finish at 11, right? Because if we're looking at the backwards path, it can start at 11, and the earliest it can start is 5. So 5 here is the start, and then 11 is the maximum that it can finish, and it can take 3. So we've got here 3 kind of squares shaded in because that's how much it takes, and then we've got the float time here from 8 to 11. And so you can go through and do that for the rest. So let's have a look at D. D is this line here. The activity can start after A is finished, and it can start at 5, and it takes 4 days, so that's why it's shaded in darker for 4 days, and it has a float time of an extra 2 up to 11. So it can finish here at 11. Let's have a look at the others first. So E here is this line here, which could occur after B, and it has a whole length of 5 days. The activity of E takes 5 days, but it could finish at 16. That's the latest time it can finish is at 16. So that's why we've got it starting here at 8, which is where it starts, and it finishes here up at 16, because that's where the activity E finishes, and the latest time it can finish is at 16. Let's have a look at F. F is this one along here. It could start at 9. The earliest it could start at 9. If this was done straight after, if D was done straight after A was finished, and it was done in 4 days, no delay, and started at 9, F could start then. And it could start at 9, and then it could go all the way up until 17, so it could finish it on the 17th day. So our F here has a time of 6 days, has to be completed, or it takes 6 days to complete it, and it has to be finished by the 17th day, and then so on for the other two, G and I. So the same person, if we were to look at these two here, B and D, the activity, the same person can't do these activities. That's an assumption that we make. We assume that only one person can do an activity at one point in time. They can't multitask. And so, yeah, that same person here can't currently do the same thing. So we would at least need to have 3 workers, because there'll be someone here doing something, someone here doing something, someone here doing something. But what happens if we start moving activities around to kind of shuffle them so that we can make the least amount of workers? Because currently we're looking at, if this was how it was going to flow, all of these people would have to be different workers at different times, and that wouldn't be the best use of money. We could actually just move some of these along their float times so we can get one person to do more than one activity. So like here, if we were to move red across, to here, we still can't get B and D to do anything, unfortunately. But what if we started shifting some of these ones around? So having a look at B, if you were to leave B to start at this time, and if you look down at E, if you were to shift E up to here, it actually fits, and a person could work on B, finish the B project, and start on E straight away, like this. And that means that one person could continually be working from day 5 all the way up to day 13, non-stop working, and we wouldn't have to find anyone else to do activity E anymore. And the same person for B could be doing that. And then you can go have a look and keep doing those along, like so. Let's have a look at this one. If you're looking at D, because this one we couldn't shuffle anywhere to fit up here, this one's going to have to be another person anyway. So if we look at the end of this, we see that F, if you just move that straight up there, will fit in perfectly. So person 2 would work on D and finish F, or work on D, once that's finished, start on F. And then same for the next one. If you look at G, this one here finishes here. So you could slide I up and there, and then you would figure out that this is all the activities all being done with no gaps, so no extra float times around. And so person 1 could work on these 2 activities during this time, person 2 could work during these activities this time, and person 3 could work on these activities this time. We couldn't have multiple or one person doing both of these. So what happens, this information here tells us some important things. It tells us, 1, how many workers we can get the project done with. It tells us when the most amount of people will be on the work site, and it tells us that we can get the whole project done within the critical path time, which is what we would assume anyway. So we need one last person to do all the critical activities. There are no overlaps in them. This is all the activities covered. So that's meant to be person 4 there. So we need at least 4 people to complete the project on time. Person 1 would work from 8 hours between 5 and 13. Person 2 would work 10 hours between 5 and 15. Person 3 would work 8 hours between 10 to 18, this one here. And then person 4, or you could probably even write this as person 1 and then change all the others, but person 4 will work 24 hours between 0 and 24. Alright, and then the last thing you kind of look at is, if a supervisor was to come, he wants to see the most amount of people he can, right? So when would be a smart time for him to come? So you'd look where all 4 people overlap, potentially. Sometimes it would be that, let's say G was moved along to here, he might have to come twice for a visit, or you just wouldn't see person 3. He would just see person 1, 2, and 4 in this section here if G was over here, and he's seen the most he could in his one visit. But because all of these overlap, if a supervisor was to come between the 10th day and the 13th day for 3 days, if he came for those 3 days, he'd see all 4 workers going, and he would be able to get around and see how they're going with the project. So if you were asked when would be a good time for the supervisor to visit, you'd say between day 10 and day 13, because that's when all 4 workers will be on the work site. Sweet. So let's have a look at another example, which is this one just here. And I'll go through step by step on how we create it. Here we are. Here's our activity network. And now we need to go through and first find our critical path analysis. It will be found by using the double dominoes. Because we've already got the forwards and backwards paths method, let's have a look at the double dominoes. So here's the double dominoes. So 14, 14, 11, 11, 6, 6, 2, 2, and 0, 0. So our critical path will be B to D to H to J. H to J. And now our first step is to put the critical path at the top of our Gantt chart. So the first activity is B, which lasts for 2 days, and then we've got the next activity, which is D, which lasts for 4 days, and then our next activity is H, which lasts for 5 days, and then our last activity, J, lasts for 3 days. And then you can go ahead and just highlight those different colors if you're on a computer, or if you've got a highlighter, it's probably easy just to go through and color them in, just to make it easy to see. Alright, and now you can add in your non-essential activities. So for A, it could start at 0 and could potentially end at 4, but we know it only takes one thing. So A will be here, this will be our solid colored one, and then it could finish by 4. That's the latest time it can finish. Alright, there's A, and then have a look at the other one. So C could also start at 0. So C also lasts for 1 day. Alright, have a look at the others and then go through and fill out your Gantt chart. So G would be start at 1, last 2 days, and could be finished by 6. Once you've got all your non-essential activities in, then you can rearrange them to find out how many workers you need there at the time. So just play around by sliding them up and down and see how many you can fit in. So we can see that there is only a need for 3 workers here. You may have rearranged it slightly differently, which is fine, but you should have still got that there's only needs to be 3 workers in total to complete this job. Alright, thanks guys.